Time for another revision video. Got asked about, well, a combination of things to do with halogens. These three things. So the displacement reactions between halogens in solution and halide ions in solution. It is done at GCSE, but it is also in the A-level course, so you kind of need to be able to make sure you can do that. There was a little additional thing in there which we'll do. The halide testing, again lifted out at GCSE, but with a little bit extra put in with the ammonia addition. These, for the course that a lot of people know that I might be teaching at the moment, are Core Practical 5 and Core Practical 6. They have probably got different numbers in different syllabuses. I have to say they are fairly common to all A-level courses, so they are a thing that doesn't matter which board you're doing, you're going to need to know. And then similarly, but not a Core Practical, the making of hydrogen halide gases. Hydrogen halide gas is produced from solid halide salts. There are two choices of acid. You need to know the chemistry of one of them in more detail, so we'll go through that. I just need to get the board ready for the first one, so we'll just do a little snip and I'll see you after the join. So take the first of those, halogen halide displacements. It's all born of the reactivity within the halogens. It decreases as you go down. So it decreases as you go from chlorine down to iodine. You could include fluorine in that, but kind of tend to avoid fluorine at A-level pretty much most of the time. And so all you do is you put two solutions, or you have, in the case of this one, you would have potassium iodide solution and you would have bromine water. You put the two together and there will be a change, because bromine is more reactive than the iodine, or in fact it's to do with these half equations, we'll come to that in a minute, and therefore what happens is you get that happen. Now, balancing wise, you can't make iodine as an no, silly me, don't need that. So you can't make iodine as diatomic without having a 2 there, and that means you've got to have a 2 there because you've come from 2 bromines in a Br2. Tend to find them as ionic, so it will be 2 of those and then 2 bromides making that. State symbol wise, everything is aqueous. I'll save time by not doing that. Now, also, it is a combination of these two half equations. Bromine being more reactive will take in electrons. It will force the iodide ions to release the electrons, and therefore you sum those two together, the electrons cancel out and you get that equation that is here. There is also the addition of a non-polar solvent. So when you do this, you mix together your two chosen solutions here, and then what you do is put a little bit of non-polar solvent on the top, and then you bung it, shake it, and it picks up a colour. The reason you do that is that strong bromine solutions and weak iodine solutions in water kind of look the same colour, certainly to someone with poor colour vision like me. So what you do by putting the non-polar solvent in is you get a distinct colour for the two that you're going to see. You're never going to see chlorine produced as a product in an A-level chemistry session because you're not going to use the fluoride. And therefore the colour of bromine is distinctly orange and the colour of iodine is anywhere from pink to very intense pink, which looks like purple. So the purpose of the non-polar solvent is to just clarify which of the halogens has been displaced out. Although if you know your reactivity, I suppose you kind of know. We're going to move on to the next bit and I'll see you shortly. Okay, halide testing. The method is identical whether you're testing chloride, bromide or iodide. First thing you do, dilute nitric acid. Dilute nitric acid is merely added to remove things that will give you a false test. Now, most of the time that's going to be to do with carbonates, because when you put the second part in, carbonates will give you a precipitate. When you put it in, you get silver carbonate as a precipitate, and that would be a false positive, because if there were no chloride ions present, you would appear that you were getting a white precipitate, and that's not what you want. So what you do is you clear out the way anything that will cause a precipitate by making it into a soluble nitrate. Then you add the silver nitrate. Silver nitrate produces a precipitate of a, I wouldn't say a noticeably distinct colour, but there are three colours to learn. I maybe be speaking for my lack of colour vision there. And then you can confirm what's happened using the right type of ammonia for what you think. So here's a summary of what you would do. You would, by doing the first two, the precipitate would be white if you use chloride, off-white or cream, and you can use either descriptor for the bromide, and you get a more coloured precipitate for the iodide, which is termed pale yellow. I have to say then, these two I sometimes struggle with, but that's just depends on your colour vision. But these are what you need to learn. What happens then is you can confirm it using two different types of ammonia. Dilute ammonia will dissolve silver chloride, because this is going to be a precipitate of AgCl. And when it dissolves in dilute ammonia, it's the only one that dissolves in dilute ammonia, it forms this ion here, Ag, two ammonias. The whole thing is plus because silver is a 1 plus and ammonia is uncharged, and it goes into solution. If you do this with bromide, this here, which is a pale but noticeably more coloured precipitate of silver bromide, it won't dissolve. At least it won't dissolve if there's a reasonable amount of it. If there's a tiny amount of it, it might go. But if there's a reasonable amount of it, it will not dissolve in dilute ammonia. But if you put concentrated ammonia in, it goes and it forms this ion again. So it's something to do with the solid. When you do this here and you get silver iodide, wonderful substance though it is, doesn't matter what type of ammonia you put in, it resolutely at its pale yellow colour stays as a precipitate. So you've got two ways of determining which halide you've got. Now if you know which one you started with, that's kind of not the point of this, but the whole point of this is that when you get an unknown substance, and there are core practicals that have the identification of unknown inorganic solids, this is one of the sets of tests that you would use to confirm, have I got a halide or have I got something else, because it gave you negative tests. So this is something that you need to learn. You might want to pause and write it down if you haven't got it or you can't find it, and then we'll move on to the final part, which is a little bit more complex because of all the ins and outs of what goes on with the different halogens. But I'll see you after the join. So, making hydrogen halides, which comes in two, didn't underline the time, comes in two forms. You can use phosphoric acid and sulfuric acid. They both have to be concentrated. So this is not pretty much 100% phosphoric acid, no water. This is like 98%. Now, when you do this, it would make sense to use phosphoric acid, because if you look at the results of phosphoric acid, you only get the hydrogen halide. But the issue with it is that you don't produce them very fast. It doesn't produce them in very large quantities. Sulfuric acid is a bit more pokey at getting these gases released. Unfortunately, it only produces pure HCl. When you try and do hydrogen bromide and hydrogen iodide, you get all sorts of other things going on. So this would make sense in terms of getting pure products, but this is what you get asked about because of the way these reactions work. For these two, you get asked about that in A-level chemistry questions. Now here it says KCl or NaCl. Some people think, oh, do I have to use potassium or sodium salt? It doesn't make any difference, because the sodium or potassium is passive in what it does, it doesn't have a role to play. So it is just the halide ion that is doing the chemistry, so the metal ion is irrelevant. So we have to do this because A-level chemistry courses ask about the reaction. So what goes on? This is not a redox reaction, this is merely just kicking out the hydrogen halide. The formation of HBr and HI in those is also not a redox reaction. There is no change in oxidation state of anything. However, these and these products here are the product of the redox reaction. And the reason you get differing reactions taking place is that iodide ions are better reducing agents than bromide ions, which are better reducing agents than chloride ions. Chloride ions is so poor as a reducing agent it can not actually undergo a redox reaction under these conditions. So here you get bromine and sulfur dioxide. Now you can see the bromine, it's orange and it comes off as an orange vapour. So this comes out as a sort of white misty fumes, and you can detect the presence of any of these using ammonia. Ammonia gas, which means you have a bottle of concentrated ammonia which leaks ammonia gas into the air. That will react with HCl and produce white smoke. It will react with HBr and produce white smoke, and it will react with HI and produce white smoke. However, when the HBr comes off, which is like white misty, you don't see it as white misty because it's tainted with bromine vapour and comes off as an orange vapour. It's in there, but this is obviously coloured against not coloured, and so it makes it look like it's coloured. So you would see that, you would not see that, but your nose would tell you it's coming off, because you can smell sulfur dioxide quite distinctly. It's quite a distinct sort of egg-like smell. And when you do this, iodine, everything tends to go black with the iodine, so you get the HI come off, but actually in quite small quantities. And you get iodine coming off. Most of it comes off as it's a sort of black, almost black, but browny black solid. You get a little bit of purple vapour if it's got warm enough to lift the iodine out. You get hydrogen sulfide, and hydrogen sulfide is really toxic, but your nose is incredibly sensitive to it, so you will detect very low levels of that in the air. This is why they say you should do these in a fume cover, because of the H2S. You will sometimes get some sulfur dioxide produced because it's a sort of intermediate position in terms of redox between getting to here, so you get some of that leaks out before it gets a chance to be reduced. So if you do that, you get all these mixed up products here, but you have to be able to write equations for the production of these as well as these additional products for the bromide and the iodide. So we're going to go through the equations for those. I'll see you in a moment. So in terms of reactions or equations, the chloride reaction is fairly straightforward because you just produced HCl. All you do, displace one of the hydrogens with the sodium and you make HCl. That's a gas, and that's the production. You get a similar reaction with sodium bromide and sodium iodide to produce the HBr or the HI. You do that, but what happens then is, because of the reduction ability of the bromide, it then undergoes a reaction which is not balanced. We'll complete it in just a second. It involves these two half equations. So two bromides releasing 2 electrons to form the bromine, and then sulfuric acid reacting with 2 H+ ions and 2 electrons coming from here produces sulfur dioxide, and because you've got 2 hydrogens, another 2 H+ there, you get 2 waters. So you look at those and you go, same number of electrons in both half equations, that means you can just collapse them together. So that means that it's going to be two bromides coming from 2HBr, single H2SO4, and then what you get is two of those. And so you put all those together and, well, there's your reaction. And it's about condensing together half equations, overall balanced equation. I need to clean the board to do the iodide because there's a little bit slightly different. And I'll see you after the join. Right, last bit. Sodium iodide reacting in much the same way as we said with the, well, we said it already. Thought I'd put what happens with phosphoric acid up as well. It is literally identical in terms of what goes on. One of the hydrogens is replaced by the potassium, so you get K, H2, PO4 and HI produced. Now when you get to the additional products, there's the reaction. I've balanced it already this time, so it's quite a reasonable size balancing number of 8HI. But then the reason for that, sulfur there, oxidation number 6, sulfur there, oxidation number -2. That's a change of 8. So you're going to need 8 iodides to change, because they're only changing by 1. Now you can see the oxidation number changes in here. There's the sulfur at 6, the sulfur at -2. And that's why it needs 8 electrons, because there's an 8 drop in oxidation number. To match that, you're going to need that 4 times, because that will then produce the 8 electrons that you need there. Or it will produce an oxidation number change of a total of 8, because each iodine goes up by 1 and you need to do that 8 times to do the 8 drop in oxidation number that you have in this half equation. So when you piece that together, that's what you get. Now last time I did kind of ignore the hydrogen. You've got to remember that there are hydrogens in the hydrogen iodide and they become the H plus ions that you need there. So that was similar with the bromide. And that kind of brings it all together really. Would say yes, you need to be able to produce these equations under exam conditions. Most likely in a paper 3, because it's a practical thing involving core practicals which are examined in paper 3. However, you never know, exam boards are a law unto themselves, but I think probably paper 3 is a likely thing. So that's a summary of the most difficult one because of the big oxidation number changes of 8. You need to practice yourself at writing the equations. You might need to rewind the video and make some more notes. Entirely up to you, it's a revision video. I'm not trying to teach you anything you haven't covered already. There we are. I look forward to seeing you again soon. See you soon. Bye.